Very happy to serve in a dual role today, not only a delegate but also a speaker. And as Fred mentioned, I do sit on the board of directors of the SNIA. How many of you are familiar with SNIA as an organization? Oh, almost everybody. That's great. Good. So I'll spare you the overview of the organization. We're actually in our 22nd year now, believe it or not, in SNIA. So that's great. Now, in real life, I am president of my own firm called Advanced Computation and Storage. As Fred mentioned, was a technology exec at a number of firms, including Micron and EMC. And then storage tech and control data. Before that, I started my career as a software developer, writing code for the supercomputers of the day. So I'm dating myself there, but I wrote code for the likes of the CDC 6600. So you can look that up in your Wayback Machine. But I'm not going to talk about my company or anything else. I'm talking on behalf of the SNIA. And in particular, I've got two topics for you. This is the first of two, all about persistent memory. And then in particular, a type of persistent memory, which again, you may or may not be familiar with, called NVDIMMs, or non-volatile DIMMs for short. But I am happy to engage in dialogue with you about the current and future state of memory, no pun intended. And then I'm going to dive into, in the last 30 minutes or so, a topic called computational storage, which sounds like a bit of an oxymoron, but it is the concept of moving compute literally into storage devices. So that topic is now emerging in the SNIA, and I'll talk about that. So most of this is, all of it's vendor neutral, first thing. That's part of the tenet of the SNIA. We can talk about vendors, but I don't endorse any particular vendor of said technology or anything like that. So take that for what it's worth. But we'll cover a lot of, and again, ask questions. Most of this is educational. It's designed for the audience to ask questions, so feel free. There's no stupid questions, by the way. There's only stupid answers. I'm not going to give you any of those. So feel free. Okay, so a little overview and then talk about NVDIMM, and then we'll conclude and start talking about computational storage. So let's talk about persistent memory. So who remembers a thing called ferrite core? Who wrote code for ferrite core? Yeah, see, a couple of hands up, including mine. Yeah, ferrite core was a wonderful thing. You could literally see it with the naked eye. Teeny little ferrite core rings with at least 3 wires going through them, sometimes 4, in different directions. And guess what? Ferrite core was persistent. Right? Once you magnetized the core, you were good. The funny thing about ferrite was, you've heard about memory which is destructive write, like DRAM, where you have to keep refreshing it, right? Well, ferrite core turned out to be destructive read. If you read the bit, you had to refresh what you just read. Right? Once it's written, it's permanent, right? It's persistent, but reads were destructive. It was kind of interesting history. But we're well beyond that now, except we are going back to the future because we now, again, have persistent memory 40 years on. Right? So guess what? Now a lot of people have to think differently because memory is not just a cache, it's not volatile, it is now persistent. It effectively is storage, as we know it. So there is convergence going on in the memory and storage industries. Again, it's fairly blurry now, which is actually a good thing, no disparagement intended. And starting from today, if you like, on the left and moving along in time, I think we're about right here, as it turned out. This slide was done actually back in 2016, so today is actually reflective of about 3 years ago, when the world was DRAM and other. Others meaning peripherals. I remember Dr. von Neumann taught us in the 1940s about the world of peripherals, right? They had a central processing unit, that's why we call it a CPU, right? And then we had memory attached to said unit, and then we had peripherals. And there were lots of them, even back then, tapes and drums and things like that, and designed for sequential I/O, read data into memory, and then compute.
But it was also central processing, if I remember rightly, because quite a few of the peripherals had their own processors.
No question about it.
So you had the central processor, and then
that's right. That came a little later. That actually, I mentioned the CDC 6600. That was the first machine with so-called peripheral processing units, PPUs. There were 10 of them. And they ran the channel, and they ran the peripherals, and they offloaded the CPU. That was the beginning of CPU offload circa 1962.
That's really changed.
Right, so back to the future. Right, but we're kind of here because we always had DRAM volatile. Again, persistent memory went away in the early 80s with the advent of SRAM. And then we had DRAM. And DRAM's been with us for now 3 decades, right, at least.
SRAM was great. You know, what's the,
Yeah.
you had laptops that were instant on.
Oh, absolutely.
Yeah.
I mean, SRAM is now relegated to level 1 and 2 caches inside of processors because it's just too darn expensive. And it's also not dense. SRAM is a 6 transistor cell. It's actually bulky to hold a bit of data, but it's fast. Right? It's single nanosecond bit access. It's awesome. Right? But it's really expensive. That's why you don't see two. If you take a look at a modern CPU, about half of the surface area is actually SRAM in that process. So there you go. So we're right here. We have DRAM, we have persistent memory. There are lots of different types. Again, this is not a lecture on the different types of persistent memory, but just know that there are several of them that are on the market today, including 3D Crosspoint, which is branded by companies with a different name, and then including also magnetic RAM. There's at least 2 companies that are now producing MRAM on the market, available, right? Persistent, right? Just as all these other technologies are, but there's a flood of technologies which some are persistent, some are not. So who's heard of high bandwidth memory, HBM, or HBM2? Yeah, the GPU folks love this stuff. It's actually DRAM, but it's organized and delivered to a processor in a much different way than DRAM is in a server. It's serialized access, not parallel. So it's extremely fast, right? It's 4 or 5 times faster than DRAM in a server. So HBM is a wonderful thing. This is one reason why GPUs can do so much work, right? Small area, but lots of work in there. And then there's resistive RAM, it's phase change. And this so-called managed DRAM, which you all have in your phones, it's actually a hybrid of DRAM and NAND in a single package, as opposed to 2 packages, which takes up more real estate, and the phone people like small. So you get managed NAND. So anyway, we're right here, and then I think we're going to see OPM, or on-package memory, right? Literally DRAM or persistent memory on the CPU itself, on so-called on-package, right? Remember Intel Knights Landing? Any of you ever used that processor? It didn't last very long. It came on to being in 2013, 2014. It was a big hit because it had on-package memory, right? It actually had DRAM and as effectively a level 4 caching mechanism. There are 8 little DRAM packages around the CPU die, and they called it MC DRAM, right? I like to call it McDRAM, like McDonald's, right? So it's McDRAM. But anyway, so we're going back to that though, on-package memory. And this is beyond SRAM, this is persistent memory on-package, right? Which is, again, a really interesting concept. Because everything today on a processor is volatile. Everything. Right? Registers made out of SRAM, SRAM made out of SRAM, you get the idea. Right? So, and then, we're going to start to see this again, and you can see the trend that storage, as we know it, block storage starts to fade. It doesn't go away, but if you're computing, you're going to take advantage of much more memory, either off processor, like normal DRAM DIMMs, or on processor, on package. Yes, sir?
So this framework, is it a server? Is it a compute framework? I'm just wondering because...
Yeah, typically this is, right? So a device that requires memory, right, typically is going to involve processing of some sort. Now, it could be an FPGA.
Sure. I just meant
matters.
that how should we sort of read that chart and forecast? So you're
Right.
not forecasting, just to be clear, that
No.
memory is going to eat into storage archives. You are forecasting that compute platforms,
That's right.
where memory will take over.
Processing
from storage.
elements, and then in particular manifested in some form of platform.
Okay.
Be it a server as we know it, kind of a 1U, 2U pizza box type of thing, or something much smaller.
So isn't this shouldn't this be a scary thing for primary tier 0, tier 1 storage makers?
Not at all.
Okay.
Because guess what? As you heard, at least in some of the other presentations, they're starting to incorporate persistent memory technology, which is the new tier 0, by the way. And I've got some charts to show that. Right? So they're not scared at all. They're saying, oh, great, faster storage medium, wonderful, bring it in.
Okay.
Right? So they're starting to utilize it. The question is, how do they utilize it? Do they use it as a block device, or do they use it as byte addressable? And hence the conundrum, because persistent memory is used in both. Persistent memory, by definition, very simple, right? Two-part definition. Number one, it can use memory semantics to get data in and out. In other words, CPU load store, so byte addressable, right? That's condition number one. And number two is it's persistent. If you have both of those conditions satisfied, you have persistent memory. Simple as that.
What's if we turn the table? What about the DRAM makers? Should DRAM makers fear the advent of persistent?
Well, there are only 3 DRAM manufacturers in the world. You can count them on one hand, right? Their names are Samsung, SK Hynix, and Micron. That's it.
SNIA?
What's that?
SNIA.
Well, yeah, but
Very
you know
small.
they're owned by other companies and whatnot. So I don't count them, right? Because they're, you know, the mosquito on the elephants, you know what. So anyway,
The 4 are the major.
right. And then there's 4 major NAND manufacturers, right? So the universe is quite small. Right now, all of Samsung, Micron, and Hynix are also investing heavily in persistent memory.
Okay.
Because they can, because they've got the fabs and, you know, the engineers to do it.
But in this vision you just charted, DRAM is giving up, giving up room and space and share
Right.
to other technologies. NAND, persistent.
Sure. Absolutely. Not
Storage
going
class.
away, mind you. It's still very useful, part of the memory hierarchy now, as opposed to the storage hierarchy.
But they're going to shrink as a BOM of.
Well,
compute.
let's put it this way. The demand for DRAM is cyclic, as we know, and it's driven by the hyperscalers in particular, because they place billion-dollar orders for DRAM, right? Usually in the form of DIMMs. But, so, you know, if you're, say, Samsung or Micron, you win either way. Right? So, sure, maybe the percentage of DRAM in a given server, for example, might shrink, won't go away, but now I've got extra persistent memory in it, plus the demand for DRAM is just about insatiable, right? You've got DRAM in your phones, right? That's another huge source of revenue for the semiconductor companies is mobile
Yeah, but
memory.
small change in demand could, tank the
Oh,
prices.
exactly
So
right.
even if it just dips 10%,
Right, I mean, just
they
the
can
shift
crash.
from, people ask why DRAM prices spiked a year and a half ago, they're actually falling slightly now. But it's because a lot of the mobile manufacturers went from 4 gig to 6 gig of DRAM inside a phone. Immediately 50% increase. You know, times 700 million phones, right? So now you know why. So anyway, it's converging. So the persistent memory vision is very simple, right? It brings storage into what we know today as a memory slot, right? Again, thinking a server, right? A DIMM, right? A dual inline memory module. Anybody remember SIMs? Single inline memory? Oh yeah, that was before DIMMs, right? Curiously enough, we've never had QIMM or quadruple inline. We're stuck on double.
I don't think we ever had Tim's either.
I don't think so. No, we didn't. And they didn't make the mistake of going from SLC to MLC, right? They actually called it what it was. Dual, right? 2. So anyway, so storage and memory slots, again, persistent memory. You can store data in it for the long term across power events, which is one of the big, profiles of this. So lots of different use cases. We'll go into that, but the key is fast like memory, persistent like storage. Right? It's the Miller Lite of technology, right? It tastes great, less film, if you're in the Miller Lite, which I know a lot of you aren't. You're Europeans and you don't go there. But beer is beer in the U.S. I won't comment on beer in the U.S. But fast and persistent. Right? Again, that's what persistent memory is. That's what ferrite core used to be. Ferrite core was very fast for its day. It was the fastest thing around. So again, a memory hierarchy, literally starting with, transistors in a CPU, right? Not memory, just transistors holding bits, right? Volatile registers, cache, right? Which is part of the function of SRAM today inside a processor. And then we have this large gap. Because without persistent memory, once you leave DRAM and the CPU and memory on DDR4 channels, you are now entering the world of peripherals. And don't get me wrong, I love peripherals. I oversaw part of the SSD program while at Micron. NVMe SSDs are great. But, on a good day, you might get a 50 microsecond read access, right? A cache line fill from a good memory module on a Skylake might take 50 nanoseconds. So we're talking 3 orders of magnitude different. Right? It is as if, and I tell the story at Flash Memory Summit, so I'm a Marriott guy, right? If you travel a lot, you become loyal to one brand or the other. I happen to be a Marriott guy. And so I stay at the Santa Clara Marriott. And if you're familiar with the area or been to Flash Memory Summit, it's about a mile walk from the venue. And I like to walk, and the weather is pleasant, so I walk, and it's 15 minutes, and I'm there. It's great. Don't have to pay for cab fare, right? So it takes 15 minutes to go 1 mile. Now, if I was in the world of peripherals, if I was staying at the Hotel Hard Drive, I'd be walking 1,000 miles to get to the venue, which would take me 15 minutes times 1,000, 15,000 minutes to get to my destination. Now you know why your databases are so blank slow, because you're living down here. Right? If you can live up here, now you have memory access. You're into the tens of nanoseconds. It's a wonderful place to be if you're concerned about getting work done, computing. Right? If you're just concerned about big bulk storage, great, be here all day long, no problem. Right? Just don't try to compute against it. Don't you love the phrase in-memory computing? You've all heard this, right? In-memory, you've heard of this term, right? I have news for you. If your data isn't in memory, you're not computing. You're storing. And there's nothing wrong with storing. We all love to store data. It's great, right? You store photos and videos. We were showing off our photos of our family at dinner last night, were we not? So that's storage. But I don't want to compute against that, right? Because it's down on a peripheral. Happens to be NAND flash, yay NAND, but it's not useful for compute until you move it into memory. And then and only then is it useful for compute. So that's what persistent memory does. I can store data in here immediately accessible for the purposes of compute. This is a new world. Actually, it's an old world. It's the world of ferrite core all over again, but you get it. Right? Because I talk to programmers today that are in their 20s, 30s, 40s, and they're going, persistent what? Are you kidding me? Because they use memory as a cache, right? Everybody uses memory as a cache. You read data from disk and you cache it. And you even have things like memcached, which use memory from multiple machines across the network. Great, what if I didn't have to do that? The world gets a lot simpler. I got news for you. And it gets a lot faster too, which is great. So let's talk about NVDIMMs, which were and still are the first and arguably the most popular form of persistent memory on the market today. There are 2 types. NVDIMMs, by the way, are standardized. They're standardized by JEDEC. Right, they have been for a couple of years now. And there's the N type and then the -P type. And they are different animals. They're both standardized, by the way, and then the P type is actually just now completing standardization. But the N has been on the market for about 2015. Several vendors supply NVDIMM-N to the market. Right? Effectively, it's half DRAM and half NAND. It appears as DRAM to a host. So I can go out and source NVDIMMs, plug them into my server DIMM sockets. Looks like DRAM because it is. Because the only time the NAND gets involved in this is when the power loss signal occurs. It's called ADR. All right, so CPU raises its hand and says, I'm going to die. Go NVDIMMs. So the NVDIMMs use an external power source, usually a supercapacitor of some form. Used to be batteries, but batteries are evil in lots of different senses of the word. Right? You don't like to ship them around. They fail. Murphy says they're going to fail just when you need them. So supercaps are wonderful. So the supercap provides energy and the DRAM effectively transfers into the NAND. I've got a slide on that. And then vice versa when the power comes back up. And these things work and they're standardized. It's a wonderful thing. You can buy them today. All right, NVDIMM-P, again, several vendors working on -P technology. It may or may not have DRAM in it. Doesn't have to. It could be all persistent memory. Right? So the -P vendors are at liberty, but what it does is it specifies the interface between said module and a memory channel. Could be DDR4, could be DDR5. By the way, there are no DDR3 or lower such things. DDR4, 5, and then onward. Right? The host is decoupled from the media because there's a controller sitting in here negotiating the access back and forth to the CPU. In the NVDIMM-N, it's standard DRAM controller, no problem. We've been doing this for 30 years. Right? Very simple. So there could be lots of different latencies floating around in here. If you use a certain type of persistent memory, maybe it doesn't have the latency that DRAM does, you're going to see different effects, hence a media controller sitting here in the middle. Right? Effectively, an NVDIMM-N is a simpler device. The -P is not. Lots of controller and firmware to go with it, and this is one of the reasons why it's taking longer to get to market too. The development is not as trivial as an NVDIMM-N. So this actually didn't happen, but it will in 2019. By the way, this whole thing was presented at Flash Memory Summit in 2018, and you can go online and get it.
Sorry, Rob.
Yeah, go ahead.
Sorry, just can you say the benefits of utilization of P?
Yeah, I'll get there.
Okay.
Yep, I'll get there. Thank you. You're a great street man. Okay, so again, how it works. I've got super caps. You know, they fit into a standard server DIMM socket. You power up the server. The super caps begin to charge, which is a good thing, right? You always want your caps on charge, right? So they power up, and then the NVDIMM functions as like an RDIMM does, with DRAM, until the power goes out. So literally, you could use an NVDIMM for the lifetime of the server and never observe the backup behavior if you always supply power to it. Which most data centers, that's a goal of theirs, is to try to supply power to their servers. So when that happens, right, and the power goes away, right, it's effectively armed once the super caps are charged up, it's armed and it sits there and waits for something to do. And during a loss, now the DRAM contents get backed into, they call it backup, literally, they get backed up into NAND with energy provided by the super caps. So the CPU is dead, gone, out of the picture. Nada. Right? This happens independently of the CPU.
Can
But
you
you still
do anything
lose
with
this
the NAND
machine
otherwise, or is it redundant?
Sorry,
the rest
go
of
ahead. Say again.
Can you do anything with the NAND the rest of the time?
No.
Is it redundant the rest of the time?
No,
Yeah.
it's inaccessible from the processor.
So you're actually buying two lots of memory, and you're only ever using one at a time.
Yeah, you're using one, and just in case, you've got
It's
persistence
just
on the module.
It's just it's just
Right, it's
waiting
sitting, waiting for something to
backup.
do. Right, it may never do anything, which is a good thing. But anyway, so there was another question after yours.
No, I was just thinking out loud that how meaningful that is when you lose this, you know, the the SRAM contents in the processor.
Yeah, so
you break
here's
the
the other
machine
thing.
state, you break data integrity.
Great question. So here's the other thing. When the power goes away, that's why the ADR sequence is also part of the JEDEC standard. Right? Because ADR means I've got to flush caches, and I've only got a little bit of time to do it.
Okay, so, okay, I thought you meant catastrophic power loss to the system, which
Right.
is
I
instantaneous.
mean, power loss is literally not instantaneous,
Okay,
right?
so you still have
So-
enough capacitance. in the-
Exactly, right. So
in
the
the
whole
PSU.
idea is to keep the system alive for some number of microseconds and get those caches flushed. You know, this is L1, L2,
Okay.
L3, and it doesn't take very long because it's SRAM,
Okay.
right? So it's great. So now these NVDIMMs, again, they have constant power because of the super caps.
Okay.
Great.
Okay. So the PSU will hold for enough microseconds for the memory to absorb the cache.
Yeah,
Okay.
that's a very important point. That
Yeah,
turns out to be a
sure,
big deal with persistent memory too, but we'll get to that in a
I'm
minute.
just not sure about the cache.
So again, when the backup is complete, then the super caps go, yay, done, gone. So now I'm power off. And literally, because of the size of NAND and where it is, you could probably hold this for several years in this state. All right, now don't put the NVDIMMs in the oven. It's not good for them. Normal kind of room temperature, they'll last for quite a while. Now, again, if you're a data center, your whole goal is to never lose power, of course. So, again, this is the emergency situation, but it makes memory persistent. So if I scribble into the DRAM on an NVDIMM, I am guaranteed persistence. This is across power failure. This is a wonderful thing, because when the power comes back up, guess what? My DRAM is the way it was.
It's because the flash memory just lost information after 2 years.
Well, it depends, again, on the temperature you store it at and whatnot, but I mean, you tell me a data center that would go a power out event on a server and try to bring it back up 2 years later. A, they'd be out of business, right? And B, nobody would care. They'd have moved on from that provider.
You have the same issue with normal storage,
Exactly.
and the battery or
Sure.
the capacitor
Right.
usually are for 2 weeks.
Yeah, it all depends, yeah. So again, when the power returns, we do the opposite. The NAND gets flushed because of the onboard controller, gets flushed back in there. Power is up, so I don't need the super caps. All the super caps do is charge, and we're back to square one. So this is a wonderful thing. And again, this has been on the market for about 4 years now, 2015, right? And it's, widely distributed. Here's the ecosystem. It is standardized, like I said. Now the NFIT, I don't know if you know this term, it's the NVDIM file or firmware interface table. It's part of the BIOS. Right? So again, all the server vendors are compliant to that. And since Linux 4.4 and then Windows, and I'll talk about Windows in a little bit, they've had operating system support for NVDIM. You can use them. You can use them as a block device in Linux if you want. Same with Windows too. Right? Open source library called pmem.io. You can go look it up. Lots of people are beginning to program to this. So the whole idea is twofold. Right? I can use the persistent memory, which is NVDIM form, with storage semantics if I want, like a block device. Just a really fast solid-state disk. Right? Happens to be resident in the memory channel, so I never go over the peripheral bus, but it operates like a disk because I access it in a block manner. Block address and a link. Right? Go. So there's file systems that use this. You can use a persistent memory-based file system, of which there are some. Right? That they're aware that this is actually a persistent device, so they don't have to go through all this rigmarole up here in the OS. They can just go straight to the NVDIM. It's a wonderful thing. Nice and fast. And then, again, the so-called direct access or DAX-enabled file systems. So there are a couple of examples of those. But this is a memory semantic. So the world over here is storage. Because of the way you access it, the world over here is memory. So I'm byte addressing it. Load, store, CPU, as opposed to read, write, I/O. Okay, the two different worlds. They end up in the same place. Of course, on an NVDIM, but it's two different worlds. It depends on how you've written your application. Do you do I/O to fetch data, or do you fetch data out of memory? All right, so if you're SAP HANA, for example, you fetch data out of memory. If you're some other database, you might fetch data from disk and then buffer it up into memory and cache it and try to hold it there for the purposes of eliminating latency. And then down here, it's its own little ecosystem. I got a power supply, I got energy modules, which are super caps, I got a controller, so this whole world can live on its own when the power goes away. Okay, now there are lower layers in here that most people aren't aware of, because when you buy a server, do you really care about the BIOS settings? Well, if you're an enterprise data center, you probably should, but a lot of people don't. And it's called also a piece of this called the memory reference code. So this is what happens when you boot your server. Because you have to recognize that there is a different area of memory, not just regular old DRAM, that is now persistent, and I have to tell the kernel about it. So the BIOS at the lowest level has to inform the kernel about what its memory resources look like. Where are they? What DIMM slot are they in? All that kind of stuff. Right? So it has to do this, and then this is not ARM as in processor. This is ARM as in get the switch ready to go. Right? Arm yourself for battle. Right? That sort of thing. So, and then again, this is what happens when the power goes out. You got to detect it. Right, so the baseboard manager controller says, oh crap, power's going away, and I've got to do all this. Right, flush the write buffers as fast as possible. Now, what is a fast backup? So here's a real world example. So I can buy an NVDIM that's 8 gig of DRAM, 8 gig of NAND, fairly small, and a super cap to go with it. All right, again, all these things are independent, so for every NVDIM you typically have a super cap. Now some of the manufacturers are saying, okay, we'll build a big super cap, enough energy to do 4 NVDIMs at a time, for example. Right? It's like buying a bigger battery. Right? But doing this might take, on an 8 gig NVDIM, this might take 30 seconds to either back it up, power goes out, or restore it when the power comes back on. Now, if you're a data center person, 30 seconds is no big deal. Right? If you're a laptop or a phone person, 30 seconds is a big deal. You don't want to wait 30 seconds, right? We're all impatient people these days, right? So now, the larger the NVDIM, guess what? Physics is physics. The more time it takes, the more energy I have to provide, because now my supercaps might have to provide energy for 2 minutes, say 32 gig NVDIM, 4 times 30 seconds, right? Same rate of power, but I just got to supply it for longer. So the super caps have to be stronger, and you have to do this. So you might wait, again, on a 32 gig NVDIMM, you might wait 2 minutes for this to happen. Not a big deal to some, you know.
Can the system recharge on boot? Recharge the NVDIMMs on boot to.
So as soon as the power comes on, the super caps begin to charge.
Yeah. Okay.
They don't take very long to charge, by the way.
Right.
Yeah. So, you know, tens of minutes at most. They're pretty efficient little animals. Plus, do not, I warn you, do not attempt to put a super cap on your tongue like we did with a 9-volt battery. You have no idea how much a farad is, unless you went to EE. And, you know, a farad is a lot of energy. And some of these super caps, I kid you not, right? Super cap the size of a relatively large index card, 900 farads. That would easily set this room on fire. So super caps are amazing little critters.
But essentially, you know, once the NVDIMM has done its job and gone to sleep,
Right?
you're going to get that data back because if nothing else, you can charge up the super caps.
Don't need the super caps at that point.
Yeah.
Everything is dead. Super caps have probably discharged,
Yeah.
right? Saving the data, and now you're just waiting for the AC power to come back on. Yep. So here's some stuff in the BIOS. If you actually buy a modern server, you can see this, right? In part of the BIOS and the integrated memory. Again, this is really low-level stuff, but guess what? The ecosystem has to be there for NVDIMMs to work. Right? There's lots of software and firmware enablement to get this persistent memory technology. We're there, right? So you got to configure all these things. Usually the defaults are just fine, and figure out when to trigger it and what it does, and all these type of things. Again, very nerdy stuff, but got to be there in the ecosystem.
It's very simple.
Now Linux, as of 4.4, by the way, the current Linux kernel rev is 4.20. So you can see how far we progressed. This is relatively old. Again, the Linux kernel has had NVDIMM support for almost 4 years now. Right now, there are systems out there which are at kernel levels less than this, sometimes all the way back to 2.6, which was a very popular release of Linux kernel. And you can't use NVDIMMs with that. It doesn't have the support. 4.4 or better, it does, right? Which is great. They added in 4.2, it was kind of buggy, and then by 4.4 they worked out the kinks. So that's great. So you get persistent memory devices, /dev/pmem0, which you can use as a block device. In other words, you can do read-write to it, I/O, right? In addition to using it like memory, like CPU load store. This is a wonderful thing, right? And there's two forms of direct access. In other words, byte addressable file systems in Linux, XFS and ext4, and both in the DAX variant, DAX, direct access. Right, so there's all sorts of tables in here, and persistent memory is byte addressable, so they have to figure out what form of atomic writes you can do. And again, that gets back to the point of caches. So when you do, byte addressable write into NVDIMMs, in reality, you're writing into L1 cache in a processor, and you got to flush that out to the NVDIMMs. So there are instructions in these CPUs to do just that. Some people call them the fencing instructions or the commit instructions. Right, it flushes the cache from the processor, which is SRAM, volatile, down to the NVDIMM. And once you've done that, it doesn't take very long, again, tens of nanoseconds to flush a cache line, then it's persistent. You're guaranteed the persistence, right? And again, you can always use block devices, dev pmem0, and lay a file system on it and have a nice day. And I'll show you some examples of that. Now Windows, as an OS, has supported NVDIMM-N since Windows 2016. Server edition, right? Not on desktop edition, server edition only. Right? That may change, but anyway, so Server 16 supported it. It supported it in block mode. Again, just like a really fast SSD. Didn't have to change anything to use that. Right? You still have the I/O path overhead in the operating system, which can be much greater than actually the overhead of the NVDIMM itself, typically is. Some number of microseconds here, some number of nanoseconds down at the NVDIMM. Right? And then the big kick is the direct access mode. Again, now you're doing byte addressable CPU load store to get your data moved. It's a wonderful thing. Right? No I/O, no queuing, no asynchronous. no nothing. Super simple, right? I got a buffer. I instruct the CPU, go store this, and here's your memory target. Boom. And it happens, right? No I/O, no interrupts. Wonderful thing. So there are all sorts of links for Windows users to use NVDIMM-N. And here's an example of block mode versus direct mode. This is a big difference, right? So they did some, and again, this is back in Server 2016 days. It's probably even better now. But thread count 1, I do a single thread of I/O in NVDIMM block mode, and I got 187,000 IAPS with 5 microseconds of latency, end to end. Most of that is system overhead, not the NVDIMM. But if I do direct mode, which is CPU load store, throw the same I/O stream at it, I get 1,000,006 IAPS, almost 10 times as many, and the latency is, again, 10 times less. It's 520 nanoseconds, pardon me, nanoseconds. It's kind of hard to get your head wrapped around that, because it's very fast. Because, guess what? You're doing memory operations, not block I/O operations. Right, now again, 40 years ago, we took this for granted with Ferrite core memory. We could write a byte anytime we wanted to, and it persisted. We were guaranteed. And it made OS development and file system development in particular very straightforward. Think about how databases work. Who's heard of two-phase commit? ACID. Well, with volatile memory, guess what? You must have two-phase commit to guarantee the atomicity, the A in ACID, that property. Because you're not in persistent stable storage until you get down to some form of block device. Well, persistent memory, that goes away. As soon as I do the byte right and flush cache to be safe, I'm persistent. Game over. It's a wonderful thing. Right? It's going to really impact the world of compute. So here's a comparison. If you're into different forms of memory, as am I, nerd that I am. And again, this was last year, so the numbers may have changed a little bit for this year, and or there are now more memory types on the market, which is great. And by the way, these are all persistent technologies. You'll notice plain old DRAM is not on the list.
I can't read it. It's written DRAM.
That's a DRAM. I'm sorry, the font is white on yellow. It's not good. DRAM NVDIMM. This column is an NVDIMM. Right, again, NVDIMM-N, half DRAM, half NAND. You're accessing the DRAM, but it's made persistent. Right, so there's all sorts of different endurance and byte addressability. NAND is not byte addressable. Hence, at least by the SNIA definition, it is not persistent memory. It is non-volatile memory, but persistent memory must be byte addressable by definition. So it's kind of a legalistic thing, but that's the way it is. And then a range of latencies, from nanoseconds to microseconds, a range of power consumption. So if you're a semiconductor or a device vendor, this is your engineering equation. There are literally dozens of trade-offs to be had if you're going to invent the next new form of memory. Right? You know, foobar memory. Or if you're a Unix guy like I am. I'm going to invent foobar memory. Well, I got to make all these trade-offs. Do I make it byte addressable? Do I give it super high endurance? Do I give it super low latency, et cetera, et cetera? And then the big one, of course, is price. How much does it cost? Because if it's too expensive, I don't care if you've got the best frickin' memory in the world, nobody's going to buy it. That's the reality of doing business. Right? And the semiconductor people all know this. They know it in spades. So they have to constantly trade off, because you'll notice each one of these columns has different characteristics.
Yeah, like VRAM is actually really good for pretty much everything apart from density.
That's right. DRAM is a wonderful thing, except it's expensive.
It's for the dash N.
Yeah, this is the dash N again. For the dash P,
It's,
please be aware there are no dash Ps on the public market yet. There probably will be by the time the year is out, but not yet. There's plenty of dash Ns on the market and have been for about 4 years in various capacities. And again, there's a number of different vendors that sell dash Ns.
You're including DC persistent memory from digital in that statement then?
DC persistent memory from digital?
From Intel.
Oh, for Intel. So Intel so-called Optane, or data center DC persistent memory, is 3D XPoint. That is the memory technology which Intel and Micron co-developed. Now Intel has branded it and selling it on the open market.
And that's not an NVDIMP.
No, it technically is not, because while it uses DDR4 signaling, it is not a JEDEC standard part, Chris.
Okay,
It's not
so that's-
standardized, so therefore it cannot be a -P by definition. It's like it, but you can't plug it into a DIMM slot and expect, pure JEDEC signaling to go on. Intel has done its own work there. Just be aware of that.
Are they open to JEDEC standardization? I'm just asking because it's a
I don't work for
platform play.
Intel, I'm not gonna
I know.
answer that.
Sure, they
Now,
talk to
between
them.
you and me and beer, I don't know if they are or not. We'll see.
Yeah, but because today they position it as a platform play and they're not
Well,
interested
sure.
in selling it to anyone but the Xeon buyers. That's a package. It's a bundle. It's
That's
a
what
bundle.
happens when you're a monopoly. Because again, the only source of this in the
Can't
world,
afford
at
to
least
make
currently,
money.
is now the Micron fab.
It's Micron.
That's
and
it.
Intel.
Well, they had a joint venture, I was part of that, because I oversaw
They
part of
both
that, and then
did.
they split,
That's it.
right?
Yeah.
They dissolved the joint venture, now they have certain rights until some date in 2020, and Intel can buy Crosspoint from Micron, and they can sell, do certain things, I'm not a lawyer, I'm not gonna get into it.
But the
But then after that,
It's totally different now,
So
the
it's-
way they
You're
on your own.
acting.
the Intel manufacturing
Yeah.
was sold to Micro.
Micron
Oh,
bought
yes,
out
yes.
Intel
Gone,
share.
yeah, so again, there was a
Yeah, I
joint
remember.
venture in place, and it's done at a facility called the IMFT, the
True.
Intel Micron Flash Technologies. It was a company that formed the joint venture.
Yeah.
Right, they each had certain rights. Micron could buy Intel's part of it. Intel could sell to Micron. There was a battalion of lawyers doing this, and I don't want to go back into it. That was not fun.
Rob, you
But,
said there will be NVDIMM/P parts on the market by the end of 2019.
That's my opinion, yes.
That's your opinion.
Right.
And then you said Optane DC persistent memory is not an NVDIMM-P.
Correct.
So who will deliver these NVDIMM-P
Micron.
parts?
Oh, well, you could name the semiconductor vendors, you could name the current NVDIMM-N vendors. So Smart Modular, Viking, Netlist, I'm going from memory here.
Because this is something you
Again, the people that manufacture NVDIMM-N are the likely suspects to deliver -P.
This is something you construct like a DIMM,
Oh,
not
absolutely.
something that you build like a chip.
Right.
Yeah.
So if you're a DIMM, if you're, for example, Smart Modular, who is now part of Smart Holdings, right? You make DIMMs. So you source memory from Samsung, Micron, Hynix, blah, blah, blah. And then you assemble DIMMs as a package and sell DIMMs to the market.
Yeah.
A company like Kingston does the same thing on the consumer side, right? They don't make NAND or DRAM, they make DIMMs.
But
Open
these
facility.
guys will not be using 3D crosspoint media.
So, say again, Chris.
These
sorry.
guys will not be using 3D crosspoint
Don't know.
media.
Chances are not. That's, again, my opinion.
Could you
They
use,
may use some other form of persistent memory.
could you
maybe
use
NRAM?
3D crosspoint
Oh, absolutely.
media to make an
Sure you
NVDIMM?
could. Sure you could. Absolutely.
It's just it so happens that the Intel version.
Right, so again, the preferred model for NVDIMM-N does not specify which persistent memory technology you must use.
Sure,
It's an interface spec. It's how to drive it, right? So if you, in theory, somebody could make an NVDIMM-N with equal parts DRAM and 3D XPoint. Now, nobody has done that, and I don't see anybody doing that, or maybe equal parts DRAM and MRAM. Doesn't matter. It's up to the market.
You think they'll have to use media from that table?
Well, these are, Chris, to be fair, these are the ones that are either currently in production or close to it. Now, there are others. Again, there's actually two different forms of MRAM, but I won't get into it. But there might be others on the horizon that, I don't know about, but these are, PCM, by the way, phase change memory. That's what it stands for. Right? So these are visible. Let's put it that way. These are visible technologies, either saleable or in development. Yes.
Just for my benefit, so MVDM, is that a data center specific standard or is it like more flexible and
So,
so
what's
can we
the answer? I'm
interpret
sorry.
MVDM N or
Sure.
or P
So
doesn't
okay,
matter.
those are both JEDEC.
Yeah, JEDEC, but specific for data centers or
Well, let's put it this way.
PC, or can we expect like smartphone?
Anywhere you see a DIMM slot,
Yeah.
it could be on a PC motherboard, right? All the PC DRAM these days, DDR4, Kingston, Crucial, all these DIMMs, they're also JEDEC standard.
Sure.
Now, you typically don't see NVDIMM in a consumer PC,
Sure.
right? And then there are other form factors of DIMMs, like in my Mac, I have a SODIMM, an SODIMM, right? It's about this big, and it's got a different pinout than an RDIMM does.
But is that covered under the NVDIMM specs?
No.
Yes.
No.
No. Okay.
NVDIMMs have RDIMM 288 pin connectors.
Okay, so those are the large. Okay. Now I just wanted to clarify because I'm trying to
So
understand
in
who
a
else
desktop
can reach
PC
production
could be
level.
applicable, and or a server, right? Without a form factor change, I don't think you'd see any of these in, for example,
Sure.
not in the near future.
Do you have an opinion as to which of those media technologies are likely to be used in the NVDIMM/PS?
Sure. So my opinion, not a SNIA pronouncement. This is probably going to be. This is already being used. NAND, NVDIMM-N.
Mm-hmm.
Right. There will probably be NVDIMM-P with NAND as well.
Okay.
Probably. I can see 3D XPoint being in a standard JEDEC NVDIMM-P by somebody. Don't know. Could be Micron. Could be somebody that buys the stuff from Micron or Intel.
They need to do that.
And then I can see it happening for MRAM. Because MRAM is on the market. Magnetic RAM. So like a company like Everspin, for example.
Yeah,
Again,
but
not
they
endorsing
don't
any
have the
particular-
density and
Gave
capacity
us
levels and
just
performance
before it was
levels.
this
I'm sorry. Go ahead.
Sorry.
Sorry.
Just,
No, go ahead.
no, I just meant to reflect
Because
that
they're
Everspin, they don't have the performance levels and capacity levels as far as I can tell.
Oh, well, performance on MRAM is actually quite strong. Latency is pretty low on MRAM.
Yeah.
Right? The problem with MRAM is it's not dense.
Yeah, that's
It's megabit
That's a big-
size
that's a
stuff.
big
They
problem for
just
data centers,
announced the first 1 gigabit MRAM die on the market. That was very recent. Before that, it was megabits.
yeah. So
Right?
it's
This is
orders
as
of
opposed to
magnitude.
Crosspoint, which is quite dense. Right? Not as dense as NAND, but pretty dense.
Sure.
So I could see an NVDIMM-P with some MRAM on it. Don't know, but I could see it. Now the others are still in development.
Yeah. but
Variant
it
RAM,
doesn't
resistant
matter if
RAM,
you've got-
phase change. Nobody's got phase change on the market right now. So anyway,
It's
and there
just
might
the
be
focus
other
maybe, but-
technologies on the market, again, that are in stealth mode. Who knows, ask the people at Intel, Micron, Samsung, Hynix, that sort of thing. Okay, again, a little performance comparison for you. This was done by the SNIA. It was actually done a while ago. Again, a relatively older Linux kernel, 4.10. But what they did was compare 4 things. They compared the branded SSD from Intel called Optane, which has 3D XPoint inside of it, right, as the persistent media. And then they did the same test with 3 different variants of NVDIMMs. They did a single NVDIMM, 16 gig large. They did 4 NVDIMMs in parallel, right, each 16 gigs. So, and then they did 2x2 configuration, 2 channels, 2 each, right? And this is what they saw. Again, this is SNIA testing. So the max IOPS were, as you might expect, with the 4 NVDIMMs. They got over 5 million IOPS at a latency of 1.3 microseconds. Right. So here's the Optane disk, right? SSD, 480 gig, standard issue from Intel. You can buy it today. Right? Some of the array manufacturers are starting to incorporate these things now, and server vendors too. 560,000 IOPS, 29 microseconds. Now, to be fair, 29 microsecond average access for that stream is really good. It beats the you-know-what out of a NAND SSD, but it's nowhere near the latency of an NVIDIA. It's a factor of almost 30 greater. So again, in the time it takes me to do 1 I.O. on an Optane, I can do 30 I.O.s in an NVIDIA. Put that into your database.
Why is Optane so slow?
Well, compared to persistent memory technologies, and you're also going through an SSD interface.
Yeah.
Even though it's NVMe, God bless NVMe, you're going down the bus, you got to interrupt the processor, you got to context switch, you got to go down the bus, you got to fetch from Crosspoint, you got to put it back up in the bus, you got to DMA it in the memory, and then the thing can raise its hand and says, done! That takes 29 microseconds. I'm doing CPU load store here. Pretty easy. Makes a big difference. Again, I love Optane SSDs. They're wonderful, right? But there's just no comparison to doing NVDIMMs. None.
Yeah.
So this is how I improve. Again, it's byte addressable. You know, for example, databases can now be fully constructed, persisted in memory. So I don't need to do two-phase commit. I just do CPU write flush. Done. Easy, right? Direct access removes all disk I/O. I don't have to issue I/O to get records out of my database. I just do CPU loads from an address. Simple. So this is, again, dramatically faster than even the best SSD solution. Because again, it's funny. It's what I'm not doing that makes it fast. Right? I'm not going over the bus. I'm not issuing, kernel context switches. This is a wonderful thing. Right? This is literally, you're in your universe with your processor and memory, and you're doing load store, and life is good. The way we did it 45 years ago with ferrite core memory. Because that's, by the way, that's how we did I/O drivers, was ferrite core memory. And then if we got really tight, we would flush ferrite core memory to a block device, which took forever. Or if you remember your 9-track tape days. Took a long time. So anyway, but it looks like DRAM to the system. That's a wonderful thing. So I can do RDMA in and out of an NVDIMM just as well as normal RDIMM. Fun. Right? Everybody's talking about, our Rocky, right? RDMA over converged Ethernet. I can send data from an NVDIMM over that protocol just as well. Great. So again,
Basically, it's an RDIMM with built-in backup.
that's right. It's a persistent RDIMM, if you like. Guaranteed persistence, right? So, the hero numbers are here. But even streaming data, right, can be taken advantage of. So if I can stream it over a network and fill memory relatively quickly, I don't have to use memory as a cache. Once I've got it in persistent memory, it's there. I can reuse it too. Instead of having to refetch from disk because now my volatile cache is too small and I got to empty it out and play the whole cat chases tail game.
So would it be very useful for the intelligent age sort of thing, where you just want certain memories to be used again and again?
Yeah, I think so, if I understood your question correctly. These are some of the use cases which SNIA has been, putting out there. So in-memory database, this is kind of, as the kids say, this is the use case, right? Of course, this would be a wonderful thing, right? But even traditional database, which Microsoft has demonstrated, because the key to a traditional database, if you know your database management systems, is to write the log or the commit log, and then and only then you get out and start to persist. But I got to get it in that commit log as quickly as possible. That mitigates the performance. So if I can do log writes in persistent memory, this is a wonderful thing. Plus, I can always roll back because it's persistent. I don't have to fetch from disk to roll back. I got it all in memory. Just the logs, just enough, to get it out there. Right? And then, of course, enterprise storage, again, you've seen vendors now start to take advantage of persistent memory inside of enterprise storage arrays, typically closely coupled with a controller of some form. And maybe it's actually in DIMM slots as memory, or maybe it's being used as a block device, like an Optane SSD. So this is starting to happen. Right? It's a wonderful thing. Right? And then high-performance computing, again, the world I grew up in. Right? They have this thing called checkpoint restart, where the whole goal is, let's say if you have a long-running job, takes 60 hours to compute. Right? Back in the day, we had to do checkpoint restart because the MTBF of the entire machine was like 8 hours. CDC star 100, 8-hour MTBF. If I could get a shift done on my star in 1980 and not go down, that was a good day. And then the maintenance engineers came in and did their thing. Right? Well, today I want to do it just so I can restart the job at some convenient interval. So the whole trick is to dump memory as fast as you can to a persistent medium. Because this is all based on DRAM. Well, guess what? If I don't have to dump memory because my memory is persistent, I can just continue to compute. There has been tons and tons of research and development, at least in the U.S. national labs, like at Sandia, for example, on this very topic. They call it burst buffers. You can look it up, burst buffers. Right? I want to burst memory into some flash device to get it persistent just because it's there and I can come back to it if I need to. Right? Most of the time you don't, which is great, but if you have to. So what's the outlook for this? So again, this is kind of a market slide, and again, it's not vendor specific. The SNIA doesn't go there. Right? So here is, we're here. Here's the next 4 calendar years. And we think at least, again, that the total of NVDIMMs, right, are in the blue bars. So the total of NVDIMMs up here may be 5 million by 2021. This is, DIMMs distributed. Now again, this number pales in comparison to other forms of storage. I mean, you heard the Western Digital people, tens of millions of hard drives a quarter. Right? So this number isn't very high, but still, 5 million NVDIMMs out there, and then the servers that those go into, a lot of them will be 4-socket and more. Right? Some of them will be 2-socket deployment, but a lot of them will be 4-socket, we think. Right? Because if you're going to have a big, beefy compute machine with 4 sockets in it, you're probably going to want some persistent memory in there, at least some, if not all.
These are going to be NVDIMMs.
Could be either one, Chris. Any form of NVDIMM. Right? The advantage of P is that since it could be all persistent memory, no DRAM, it can be made very dense. So I might have a P, for example, which, throwing a number out here, could be 512 gigabytes.
But what's
Just
your
saying.
personal, take on the split between the future, uptake between N and P? Because I would have thought that, we've had what we classify as N, maybe it wasn't standardized, but those have been around for a while,
right,
and
they
not much has happened as far as I can
Well,
tell.
again, the adoption rate is fairly low.
Yes, so my point is that I would think the P is what's going to drive.
Could very well be. I think you could be right, especially if your big concern is the capacity of memory, then the P's could be a win for you. Right? Now, if you're concerned about the sheer speed of it all, again, because P's have a controller in the middle and it's mitigating access to the memory bus, there could be additional latency. We don't know how much, again, because there's no P's on the
But
market.
those are not
to tell.
completely independent from an application's point of view, because if
Sure.
you add 8 times the capacity for the same
exactly.
money,
Right.
maybe it's 95% the performance
Sure.
per capacity, but you
Absolutely
win
right.
500%.
And it's probably going to be better than that, but
Yeah.
I agree. I mean, that is why, again, the NVDIMM-N market, relatively low, but again, there are several vendors continuing to produce, so it's at least that healthy, right? But when the P's come in, I think you're right, the adoption curve will start to go up, just because of the density of it all. Now, again, the big question is, how much is it going to cost?
You did say 5 to 12 gigabytes or gigabits?
Yeah, well, no, gigabytes. So memory is always in bytes at the DIMM level. However, don't be confused. At the die level, what the semiconductors make, it's in gigabits. Just the way it is. Sorry.
A 12 gigabyte NVDIMM sounds glorious.
Oh, I'm with you. I mean, a half a terabyte in NVDIMM-P, that sounds great to me. And I can plug 12 of them in. That sounds great. So, the question is, how much money am I going to spend for it?
How much is faster? Because the N is faster. Like,
Yeah, you're always in DRAM on the dash
Exactly.
N, by definition.
by definition.
Right. Question is, okay, how big can I make it? Again, today the largest is a 32 gig NVDIMM-N. So 64s and 128s have yet to appear, versus their RDIMM cousins, where 64s and 128s have been on the market for a while. And at least one of the big three, won't say which one, has announced a 256 gigabyte RDIMM, all DRAM.
So could you just
Get your checkbook out.
could you be just so generous and explain in maybe 5 sentences how is it possible and practical to use NAND for the P's and within P's? Because I would have thought
It's really
that's
hard.
a bit of a
It's
complexity.
going to be really hard. So they're going to
masking.
have to make a P. If somebody elects, let's say company XYZ elects to make an NVDIMM-P with NAND, I think, again, personal opinion, not SNIA, I think it's going to be part NAND and part some other form of persistent memory technology.
Okay.
I think.
So all P says.
Right, because guess what? There was, and still is, a third JEDEC form called the -F.
It was the first.
So remember Diablo?
Yeah.
Yeah.
They made a -F. I don't have to tell you what happened next. There are no dash Fs on the market, and I don't see any coming. It was a good idea, and for the time it was implementable, if that's a word, because NAND was there, and the JEDEC standard was there. So Crosspoint was not there, MRAM was not there, so I had to make it out of NAND, and they did, and you know the rest of the story. So I don't see any dash Fs appearing. The P is a much more viable option. So here's the infrastructure changes, which one could reasonably anticipate with the advent of persistent memory. And guess what? There's a lot of it. Right? This takes time. Again, the entire industry had to change when Faraday core went away and SRAM and DRAM came into play, because a lot of the OSs had to literally be rewritten for significant portions thereof. Right? But now we've lived with that for 30 years, so it's kind of the default, and people assume volatile or memory is volatile, but guess what? It isn't. So there's going to be a lot of, this is why it takes an ecosystem to deliver a new memory technology, especially persistent memory. This is not trivial. Right? The first thing that had to happen is, the semiconductor people had to do it, and then DIMMs had to be made, and then the OS vendors, or entities, Linux and Windows in particular, had to adopt it into the kernel. The BIOS people had to change. So this ripple effect coming up, right? And now can we use it inside of hypervisors and containers? There's at least one hypervisor on the market which can recognize NVDIMMs, and unfortunately they use them as a buffer cache, which is not my personal favorite, but that's how they decided to implement it. And they can see NVDIMMs, and that's great.
It's block.
Yes, and it's blocked and it's used as a cache.
Yeah, it's terrible.
Because it's persistent, you can store there. You don't need it as a cache, for God's sake. Anyway,
Do you see it?
so this is other things. Yes?
Do you see it a lot? Because I can see the benefit for containers here,
Yeah.
because they crave persistent
Oh,
memory.
okay.
So,
the go-round in storage that the container people have had to have.
Oh yeah, I
Oh.
see a lot of stupidity happening.
It's a goat rodeo.
Yeah. So,
Yeah.
how do you see the implementation there?
Oh, so a container, if you assume a container is this ephemeral thing, I spin it up, I write some data, I die.
Yeah.
It's still in memory. All you have to do is remember an address. That's it. Because if I can remember the address, the next time my friendly container comes back up, it grabs that address and says, oh, my data's there, cool, let's go. Nice and easy. So if memory is persistent, life gets a lot easier, I think, for container people. And they'll start to use it as storage.
I've seen a few people trying to get there.
Yeah, because storage is the bane of containers right now. It's awful, in my opinion. So anyway, all of this stuff, how do I allocate persistent memory to guest OSs? Again, I got a new resource out there, so remember the talk of disaggregated memory from the Western Digital. Well, guess what? How about disaggregated persistent memory? This is a whole new ballgame. What's going to happen? Okay, so again, standards. This literally allows this industry to happen. Is standards. Couldn't happen without it, I think. So JEDEC has standardized the interface for, it's a great $5 byte addressable energy-backed interface. It's supercaps tied to a DIMM, basically. Right? And then the ACPI, which is the fundamental or one of the fundamental technologies involved in BIOS and starting a processor. Right? It has to do all these things even before your kernel gets into play. So there's a lot of work that goes on during boot at the BIOS level that has to happen. In fact, has happened already for NVDIMM support to work. So all this stuff. And then, what happens if the NVDIMM starts to report its own health events, and how do you deal with that? So anyway, so ACPI 6.2 is a wonderful thing. Right? You and I can use NVDIMMs because of that. It's great. Now, last topic for this, encryption. So the good news is I have persistent memory. The bad news is I have persistent memory. So if I write something, it's there. Literally, it's there. And even if you Panama papers the thing and literally rip the DIMM out, right, flush the power, rip the DIMM out, I got bits. If those bits are in the clear, you have the same problem as you do with a block storage device with bits in the clear. Because I could plug that sucker into a JEDEC standard DIMM slot, power it on, read it.
You have a USB stick.
You got it. It's a portable storage device. Now, chances are people won't be stealing DIMMs anytime soon, but you get the point. right? Since it is persistent, now I have to worry about things like encryption and security. I can't just order the DRAM to blow itself up, right, like Mission Impossible.
People have been stealing DIMMs for a long time.
Oh, I know, and hence why we're on this, right? So, and there's all sorts of, required, mandated encryption. If you're going to store data, not data in flight, but store data, you must encrypt. That's the law, right? So guess what? You got to do this in your NVDIMMs too, because you're storing data.
You got to have hardware encryption.
Yeah, exactly. And how fast does it work? And where do you put it? Do you let the host CPU do it? Do you have an NVDIMM controller do it?
Where do you store the keys?
Oh, yeah. And then what do you do with the keys? Right? Well, guess what? So with block access, the controller can do it. Right? Pretty simple. But if you do byte access, you're up in host land. Because the NVDIMM controller doesn't know anything about bytes. It's just passing it through. So the key with the host to do backup with encryption. So if I've got encrypted data and I want to back it up into NAND, it's not encrypted, I got to have a key. What do you do about that? So all these topics are on the table for NVDIMMs. Right? So the whole trick is, during a power loss event, I got to encrypt the data in DRAM, if it's not already so, on its way to going to the NAND.
Make sure the key's stored.
Yes, sir. Again, just think of, SSDs or USB sticks with data persisting on them. So you don't have to worry about that with RDIMMs, because the minute you take it out of the slot, poof, the transistors go, I don't have anything anymore, sorry. So here's the takeaways again. We the SNIA are seeing workloads being re-architected. This is happening, which is a good thing. And by the way, the SNIA has an entire NVM programming model, right, which is a framework for developers. In fact, at the recent Persistent Memory Summit at which I hosted, we had a hackathon sponsored by one of the major hyperscalers. We had 25 programmers writing code according to the SNIA NVM programming model. Because they had never encountered persistent memory before, and they're like, this is cool, and they started to hack. And they wrote some really good stuff. So again, the reload times could be significant depending on the application. This is reload after power event. Lots of new persistent memory technologies coming out. Right, again, with the advent of, you don't have to be a vertically integrated fab. You can design a chip and then have somebody else fab it for you. Global Foundries is an example, right? So there are companies that do that. They design chips, but they don't make them. They let somebody else make it for them, right? So this could be really interesting in the next 5 years, for sure. And then standardization helps adoption, no question about it. So we have a persistent memory group and an NVDIMM SIG, special interest group, just thinking about NVDIMMs within the SNIA. And now, as you might imagine, their focus is on the -P variant because it's starting to happen. And I sit on the board, again, we watch this closely. It's a great area for the SNIA to be in. So we're helping to propel that and doing events like Persistent Memory Summit. Okay, so you can look all this up, SNIA.org/PM, right, for persistent memory. And you can see the charter and all that fun nonsense. There is a TWIG, or technical working group, that has been formed within the SNIA with several member companies, and I'll show you the logos of this, but I want to introduce you to the topic. Now, the interesting thing is this is actually not a new idea. I mean, I can't remember which one of you, Brian, maybe it was you, that talked about moving the compute to the data. Right? So, in 5 words, that's what this approach is. Can we put processing elements within a block storage device? I think we can, and in fact there are several, you'll see it, there are several companies that are embarked on just that. And actually, while I was at Micron, we had a pilot effort to do that. I think we were too early because it drove the cost of the device up too high for lots of people. Now that was 5-6 years ago. Today is today. So I want to introduce the topic to you. Again, this is nascent in form, but there is a working group. So compute, meet data. Right? Basically, if you want to get a computation task done, you've got 2 choices. You can read data into memory from which a processor of some form, maybe it's an FPGA, it doesn't have to be a CPU, right? Could be a GPU too. Lots of different forms. you got to get that data into a memory, so now I can do load store semantics on it. And I can execute instructions. Or I can take a compute element and literally bury it inside, to use a term, of a storage device, which inherently has the data, and now I have to manage compute. I don't have to manage data transfer, I have to manage compute transfer. Make sense? You got to move one or the other, because I got to have compute meet data.
And this is going to get more and more interesting as we move further and further towards containers and microservices.
Yes, sir.
Because there's a lot less to move.
Bingo. Keep thinking that. Right? So we formed a technical working group, right, to show how storage, if you provide it with, and this should actually be processing, not CPU, because you could put something else, a little bitty FPGA in there.
It's PPU.
There you go. Could be a PPU.
There's a whole
Right?
bunch
Be
of
careful how
different-
you say that, by the way.
There's a whole bunch of different.
So the question, okay, if you're running a commercial application or an open source application, how do you redefine that to take advantage of this? I've got compute somewhere else besides the CPU. Can I leverage it? So this was literally, believe it or not, a 7 a.m. Birds of a feather, that's a BOF, right? This is the first session that we had. We actually had it at Flash Memory Summit 2018. And there was a bunch of people involved. And literally that many people woke up at dark 100 to attend this at 7 in the morning. So my hat's off to them.
Why did this have to happen at stupid o'clock?
Because
Everything else
between
was
8
booked.
o'clock and normal kind of convention hours, the actual Flash Memory Summit show was running.
Okay.
So this was a BOF. This was like people interested in a topic informally getting together. Right? But there was a fair amount of people, and you might recognize some of them. Stephen Bates and other SNIA people were in there. So, that was the first ever session, and this is what they were asking themselves questions. Can we create a design to solve problems, right, by bringing compute into storage? Is it possible? Is it feasible? Is it cost effective? Can we pull it off at all? Right? And then, therefore, greatly reduce I/O traffic over a bus. Because if I got a compute element down on a bus device, I can just instruct it to do some work, and it doesn't have to fetch data across the bus. It's got it.
So essentially an architectural orchestration engine.
Yeah, exactly. Right. So how do I do all that? So to get off the ground floor, we have to have a standard way to do that, because you can imagine I got 52 different SSDs with 52 different APIs to use its compute engine. Yeah, not going to work. It's the Veritas problem all over again, right? I got 52 variants of the same thing. Doesn't work, right? So we need, and the SNIA, we're looking, to the software side for very careful guidance, because this is mostly an exercise in software. How do I orchestrate that kind of communication? Right? So they were thinking about that, and then they did another BOF at 7 p.m., so 12 hours later they decided they had so much fun they did it again. Right, and met at 7 p.m. and had some beers and talked more about this topic. Yes, sir.
I don't know if you remember, but IBM, I think in the 2005, something like this, demonstrated DB2 running on storage controller.
Sure.
In
Right.
partition.
Right.
And Hitachi, they have also partitioned.
Oh,
on the
yeah.
high
So I completely agree. They did it on, and you said the key word, a storage controller.
Yeah.
end. Yes. But
Not
the
on a storage device itself. They did it inside of a controller.
Yeah, but
So, which was very cool.
So it's an extension of a trend, because you've also got things now like routers that will run a firewall for
Yeah,
you and things
right.
like that. So it's this whole trend of distributed
Right, and it's the old
edge.
offload
Yes.
premise all over again. Right, remember TCP offload for mainframes? It was a big deal.
Ethernet,
Huge.
hard disks with Ethernet.
Yeah.
By definition,
Oh.
he's doing processing on the.
Yeah, absolutely right. So this is a variant of that, and can we extend that concept, do more processing, offload the CPUs more? And so here's the problem. So we're all CPU driven today. This is how workflows work, right? The CPUs communicate with a controller down the bus, and I got SSDs in their NAND, and you got wear leveling and garbage collection, all that stuff going on. That's all great. We know that. But unless I got data up here, I'm not computing. Got to be in DRAM. Otherwise, I'm just storing data. Right? So this, cat chases dog process can create bottlenecks. We know that. By the way, the current bottleneck in servers today is memory bandwidth. So 2-socket Skylake, to name an example. Right? I've got 12 memory channels. 6 per socket, 12 memory channels, right? I can stuff them full of 2666 RDIMMs. I get 230 gigabytes a second. Right? Guess how much of that I can shovel down to the bus? Not even half that. Do you see the problem? Right? So we have imbalanced systems. And as the core count increases, it gets worse. Because now my cores are starving. Right? That could be 96 cores in that 2-socket machine. I only got 230 gigabytes worth. That's about 4 gigabytes a second in and out of a core. Now you know why your apps are so slow. It's just not enough horsepower, at least for current standards. Right? So we can't, and also you can't scale. You could buy faster CPUs, you could buy faster DRAM or more of it, but you're still bound by the same architectural problem. Okay, so how do you fix it? Right? So I still got CPUs and DRAM, very efficient, right? But if I have an API between the processor, software, and a device, software, right? Now I can communicate back and forth. You really can't do that today. NVMe is a wonderful thing, but not for the purposes of compute. For the purposes of storage, it's awesome. Love it. Block-oriented, receiver transmitter pairs, queue pairs all over the place. It's a wonderful thing. Doesn't do anything for compute. Right? So I want to do some offloads because, hey, especially in a 2.5-inch SSD, I got a fair amount of real estate on that thing. M.2s are a different story. They're smaller. Stick of bubble gum. Right? Really hard to put significant compute on that because it's just so small. But 2.5-inch 15mm SSD, a fair amount of room. So this is good. So maybe by adding more devices with this capability, I now scale my compute as well. Remember the previous discussion about compute and storage, or you can't scale them independently? Well, maybe now you can. This is a different way to slay the dragon, right? You can disaggregate everything, or maybe you can move compute into storage. But software design is really key. Not going to work without it. So here's a taxonomy, as if you needed more acronyms. This is what these folks came up. So a computational drive, or not an SSD but a CSD, get it? Has persistent data storage and computational services. Full stop. That's a CSD. Right? And again, people are starting to make these things. Right? So I got a processor of some form. Could be a little bitty core, could be an FPGA, doesn't matter, but capable of compute. Right? And then if I put a lot of these together, I have a computational storage array. Pretty simple taxonomy. Okay, now, here's the companies that are in this. This is a pretty good list. Right? Nobody asked our friends at Western Digital about this. I was about ready to raise my hand, but I was like, I'm going to cover it anyway. So they're in. Right? Micron's in. Hynix, there's a lot. Now, some of these companies are startups you probably never heard of, but others are, mega international enterprises.
There's certainly major names missing, like a certain company beginning with in and ending with tel.
Oh, of course. Sure there is. Right. I mean, this is the nature of all consortiums. So look at, Gen Z was mentioned. So look at the list of names in Gen Z. There is a flagrant, shall we say, omission from that list. Right? But yeah, this is consortiums. You pick your partners, right? Nobody's forcing you to dance with somebody else. You just decide to align yourself with this.
I know you said that you're not company aligned at all, but there's one startup on that list that's claiming a lot of credit for SNIA's involvement.
Oh, of course.
Can you comment on that? MGD?
Yeah, so actually you're going to see an example of that. So they're, all consortiums have leaders. They are one of them. Not the only one, but they are one of them. Right. So sure, they're bringing this technology to market. They want to be profitable. They want to be a good company. So sure, they're touting themselves. So here's some use cases. So here's one from one. I've got 3 examples here. Again, not endorsing any one of them, but I wanted to show you there are different approaches to this. So here's one. And this one is involved, again, with a specific type of computational offload, and that's calculating RAID parity, or erasure coding parity. Right? Because right now, in most software-defined systems, the host, the CPU, does all this work. Well, what if the device itself could do the work? That gets interesting. right? So what this particular example was is they buried a processor that advertises, and again, this is NVMe advertising, right? I've got a namespace, except now it's not a storage namespace, it's a computational namespace. But the NVMe spec doesn't care what it is. It's just a namespace. I can advertise it. Here's the capabilities to the outside world. Go. Right? So the OS, you have to change your OS to pick this up. Again, part of the ecosystem. Right? But once you do, now I can use the built-in, this is a Linux example, the device mapper to trade information back and forth between the computational element and the device and the host. So guess what this thing does? It effectively calculates its own rate. Because the host has raw data. It says, okay, device, here's my raw data. You go forth and calculate the parity. I'm out. And meanwhile, the CPU does useful work rather than calculating frickin' RAID parity. Right? So that's a good thing. So now you can use this with normal SSDs, situation normal. This does the work, but if you have one with a controller memory buffer, which by the way is part of the PCI Express spec and NVMe spec, this is memory buried inside the device, visible on the PCI Express bus. So guess who can see it? The CPU. So this is how I send data to this. I put it in the buffer and I instruct the device to calculate parity. So this scales, because if I have n of those devices, I can calculate n different parities. And then you can offload it with point-to-point DMA and do some other tricks. But that works. That was demonstrated, by the way, at Supercomputing 18. Here's compression, similar storage. I've got a buffer of data, I want to compress it. Where do you do it? You can do it up here, or you can do it down here if you have a computational storage processing element in this device. Because again, this is one of these mathematical things, relatively straightforward algorithm that you can instruct. Again, doesn't have to be a 96-core Skylake, right? It can be something relatively small just for the purpose of doing this offload. Right? And again, they demonstrated this, right? Because a lot of apps are now doing their own compression. Because they have to. Right? They can't depend on a storage array, characteristic being there or not. So they do their own compression. Right? So, Oracle, SQL Server, a lot of the databases compress their own tables just to save space and memory. Because they have to. Right? But if you can do this down here, where the data is actually persisted, remember again, you don't have to have persistent memory up here. Right? It really helps if you do, because now you can do a lot more work here. But if you don't, now this becomes an alternate approach.
Then the application needs to know that capability is
Bingo.
there. Which
That's
it could
right.
do, of course,
And the OS has to know too.
Well, it could do that with the modern subsystem that it does compression as well.
Good. Right. And then again, NVMe over Fabric, computational storage. If I've got a compute node, either, this is either or, right? Either I can do it to the local devices, like in this example, or I can do it remotely. Because if I can speak NVMe, I can speak NVMe over Fabric. All right, so guess what? Now I have a computational storage array chock full of these devices. Maybe some have compute, some don't. Dealer's choice. But now I can do it down at the array level. So I can share a resource with this by any compute node who can see the computational namespace. And over Fabric, the default is you see all the namespaces. So it's a good thing. Right, so any of the three transports is in play. You could do RDMA, Rocky, you could do Fiber Channel, you could do NVMe over TCP. Take your pick. Right, by the way, NVMe over TCP is a thing. There's a lot of people that like it because it's cheap.
I think you've got a potential here for essentially giving people the wrong impression who are not storage specialists, because essentially everything you're talking about so far is, the data's always where it is.
Oh, right. It's always here.
But that's
right.
why computational storage might give people the wrong idea that you're talking about any business level computation rather than storage service computation.
Absolutely.
That's something you want to be just a bit aware of
Point
to avoid
taken. Yeah.
setting inappropriate expectations.
That's right. So you should come to the next computational storage twig meeting to state that opinion. Oh, no, I'm serious. Yeah, I encourage you to do so. Guests are always welcome.
Where is it?
I would have to look it up.
Yeah.
They meet once a month.
Don't have a budget.
It's usually telephone or Zoom or video conference, something like that. So they meet face to face twice a year. Okay, here's another one. video transcoding. All right, again, if you're an M&E, this is a very computationally intense task, transcoding. Right, I know, I did some work with the M&E people, and they'll take a piece of content and they'll transcode it into 57 different languages and formats, and I mean, it's amazing.
Cover Data tried this and it didn't do very well.
Yeah, exactly.
Why not?
Yeah, good question. Probably too early. That's my guess. But anyway, so there is this thing called FFmpeg, right, which happens to be an open source suite to handle video. Right? Well, guess what they did? They implemented FFmpeg down at the device level. And that's all it did. It did one, single purpose compute element. Right? And they estimated not only did they save the CPU from doing all this encoding and transcoding, but they saved 90% of the power that ordinarily would have been required to get this transcode job done. The CPUs are relatively expensive in terms of power consumption. And these things are not. Right, so they buried it inside of U.2. Again, you probably won't see M.2s, they're too small, but they buried it inside of U.2 and had this FFmpeg going on in here. And again, since the operating systems can see the namespace, it doesn't need a special driver.
Can I ask a question, Rob? You've got 3 different use cases here, and all of them have at the bottom these NVMe drives with some form of compute on them.
Right.
So these are computers. They need booting. They need an operating system.
Oh,
application code.
You're quite right, Chris.
Can you send this code to the NVM SSD and so make it not specifically dependent on one application?
Potentially. Yeah, potentially. You could have it do more than one algorithm or more than one computational
It's going to
task.
be very, very limited.
It would, I agree. It's not designed to be a general purpose approach. But if you have a specific workload, this approach has merit. I agree. I don't want to turn this into an x86. And make it general purpose so I could throw, 1,000 different apps at it.
It could be an ARM.
Oh, absolutely it could.
And then you could download stuff.
Yeah, keep thinking that.
I'm limited, I think.
Yeah. The wonderful thing is, at least with my industry hat on, I love to see the diversity of CPUs now. It's back to the old days. Remember the DEC Alpha? Right? Remember the MIPS RISC? We used to have lots of different CPUs, and they eventually withered away until we were left with one. And now the pendulum is coming back, and now we have more than one. This is like, yay, this is good.
Yeah.
Right? My opinion. Not SNIA.
But still, Qualcomm made and they recently.
I mean, go visit the folks up in Cambridge. Talk about ARM. That's, ARM Mecca right there. So anyway, the integration architecture, this is how the software stack works. Right? So FFmpeg, so I got codecs and I'm, translating down to this. Now they happen to do an ASIC down here and not an FPGA or a core. They literally buried an ASIC for this purpose, just to do transcoding. With now the other trick is they're doing it over PCI Express Gen 4. Not 3, 4. 4 has double the bandwidth of 3. It's so much better. Right? It's not 5 yet, but hey, I'll take 4 versus 3. Right? So that's really important because 4, again, is double the bandwidth, 2 gigabytes a second per lane instead of 1. So I can shovel a lot more bits up and down the bus. It's a good thing.
Really, this needs something standard on the device.
Bingo! Hence the SNIA's involvement. We want this standardized. Yeah. How do I talk to a computational element inside a storage device?
How do you stick a program on it?
Exactly. Right, so NVMe helps, again, because of the concept of namespaces. So if I got to advertise a namespace that says, these are my capabilities, operating system, you send me work as you feel appropriate. Maybe it's none, maybe it's some task. So here's another use case, third of 3. This is doing Hadoop, MapReduce in particular. We got recursive pictures. We got pictures of people taking pictures. It's awesome. Anyway, so MapReduce tasks now funneled down at the device level instead of running MapReduce all up here. So you know how Hadoop nodes works. I have name nodes, I have data nodes. So effectively, what this use case did is it created a data node inside an SSD. So this now is a fully formed functional member of a Hadoop cluster. So I got name nodes controlled by the host. But the data nodes are drives, not just other hosts, that might be doing name and data services. So this is very familiar, right? Very familiar, again. And this is drives with a computational element, and yes, they had some DRAM in this case, so they buried some DRAM in the SSD to go with it, right? Instead of doing an ASIC or something like that. And they just lined a bunch of these up. They did 8 of them, and they did TerraSort. And they saw by only using 8 cores instead of 16, they got a 34% improvement with half the cores in operation. That's pretty good, right? So they had 8 cores down here versus 16 up here, and they ran 34% better. Think about that. Fewer cores, better performance. It's Miller Lite, right? Tastes great, less filling. This is good, right? Because if you're doing MapReduce, you see this problem all day long. Now, network monitoring is another potential big offload case, right? Because this is what happens when you do network offloading today. So or networking today, network monitoring. So I get an inbound stream of data. It comes across the PCI Express bus. It gets sent to DRAM, because that's the only place it can go, because you got to process it, right? So you got to send it to DRAM, so it gets DMA'd up there. CPU works on it, and then eventually it starts storing results, or shall we say interesting events, right? And again, I'm not an expert on network monitoring software, but I do know my way around infrastructure. So that's the flow, right? So here, let's take this, same inbound stream, PCI Express bus goes directly into the storage devices, not to DRAM. And then I do some pre-processing here. Maybe not the whole thing, not the whole enchilada, but some processing. And then I can send those results up here, and I can do some really complicated things with a CPU. But if you know network monitoring, a lot of the stuff is pretty repetitive. You don't need a lot of horsepower to filter out events or, the uninteresting stuff. The interesting stuff you want to get up here instead of all of the stuff. Right? So every single packet has to be looked at. Well, if I can eliminate a lot of packets here and only send the interesting ones here, I got a big win. And then I can store it as usual. Or, since again, these are NVMe devices, I can do peer-to-peer transmission. One NVMe namespace talking to another one. So I can directly store stuff if I want to here, or send it up to the CPU. That's the workflow. So there's cost reduction going on. So again, this is a particular example. This is the processing path, right? This is the same. An application. And guess what's hiding inside these SSDs? It's a container, to your point. So I got a little bitty container doing a lot of the work here. And it's talking to an agent. Meanwhile, I've got processors going on over here, and this could change over time. But again, this is the kind of storage half of the thing, and this is the compute half of the thing. All right, so in effect, it's a computer. It's got processing, memory, and storage elements all in one.
Do you know what the processor is inside it?
In this, it's a particular flavor of core. I don't know which one. Between you and me and a beer, it's probably ARM, but I don't know that for a fact. This is from a vendor. Don't know. So, but it literally could be anything. This is just the definition. Could be, a core, could be an FPGA.
Essentially, it just has to be a Docker host.
Yeah. So it runs this, and it's a single app, right, run by a container, which is what containers are really good at doing. And here's the last use case. This is again a Hadoop work reduce, or MapReduce, I'm sorry. So you probably know that one of the most usual suspect benchmarks is this thing called TerraSort. So I generate a terabyte of data, I see how quickly I can sort it, and then I do TerraValidate at the end to make sure my sorted results are correct. And they did some testing with computational SSDs. They got this baseline for TerraSort, so they did a little over 3,000 seconds. Right, so that's like 50 minutes and change to sort a terabyte of data using normal HDDs, right? They did some compute offload, right? And they found that the baseline went down. They got a little better throughput, took less time. They did SSDs, took a little less time. Again, this is computationally intense, not storage intense, right? And then they did the compute offload and SSD, and they got it down to that number. So that was the 37% lower time to compute, and basically 160% of the jobs, the Hadoop jobs in Hadoop terms, I could get 160%, more better throughput than the normal case, which was CPU only. So they did that, and they did effectively a 9-node, again, data nodes. Again, the device becomes a Hadoop data node. So I did 9 of those, and they did 6 + 3 error correction, parity across those 9, just for redundancy's sake. So that was a good use case. And then again, compression offload. Again, there's a whole bunch of compression algorithms. They happen to implement gzip for this compression offload. And again, tying it to the controller down in the SSD frees up the host CPU. Again, the benefits of CPU offload. It's this, again, pendulum. Sometimes the offloads are great, sometimes the CPUs are great. But again, since compressed data we know consumes less bandwidth by definition, this is a good thing. All right, so if I can send compressed data back and forth instead of data in the raw, it takes less throughput. Okay, so here's the advantage that they saw with that. So they did, just CPU zlib, and then they did computational storage zlib, and they saw about a 17-fold improvement. That's a big gain. All right, so they could compress at about 500 megabytes a second down here in the CPUs, and they did, do the math, it's 7.5 gigabytes a second. It's pretty good.
Sorry. So can you help me understand how is it possible to achieve similar level of compression effectiveness when you do that on a storage device level and not on a sort of global compression level? So
Well, again, a
achieve the
lot of
same-
these compression algorithms operate at the file level,
Okay.
or maybe a set of files. I give zip a directory and say, please zip this up. It's got 50 files in it. So it operates on the files one by one and does the compression, and then you come out with a .zip. Right? That's very typical. That's what they were doing. They were offloading the CPU from doing that work. Because the disks have the data. It's there.
Sure.
Right? They have the file system already there. They know how to read the file system.
Oh, they'll have to have the disk will have to have its own memory and so on to actually do the work, or can they actually work direct on this?
Well, they need some memory. It depends on the type of processing device they have. So that's why the
They need
example
work
with a core in it had some DRAM,
Yeah.
because it wants to see DRAM. But FPGA ASIC, you could construct anything you want.
Yeah. But working RAM is really all you need.
Exactly. So I could do an FPGA that just reads the blocks into its own register set and does some crunch. And now again, you don't have a lot of space there, but you have enough to get the work done. And compared to, again, the cost of CPU, it may be a big win. So,
Especially once you add in that it doesn't actually have to move off the disk.
bingo,
Yeah.
it saves time. If I don't have to move a bit, I can spend 0 time doing so. 0 time is a wonderful latency.
Yeah.
Because we learned in elementary school, did we not, that 0 times any other number is 0. So if I spend 0 time moving 4K worth of bits or 128 meg worth of bits, I don't have any latency. It's a wonderful thing.
Well, no,
Right,
you still
so
got
that-
latency in the compute.
Yeah, that's what I got for you. I hope it was useful.
That's why we moved the query engine to the JEDAS and no more the JEDAS to the query engine.
Yeah, I mean, there's a lot of, this is just forming now. Literally, not even a year ago, August 2018, this started. The BOF got together and the SNIA said, we want to sponsor a technical working group, and you're the root set of folks to do it. So you saw the logos on there, and we're up and running.
IBM's talked about computational storage in its research labs.
Oh, sure.
It's about sort of data structure.
Right.
Things
Oh,
like that.
yeah.
Something different.
Yeah.
How does that fit?
Well, again, I don't represent IBM. I don't know for sure. This is what I know. These are the members of the TWIG, at least currently. Now, if IBM wants to join, great.
But you've not heard what they're doing.
No. Now, again, there are named entities which are not on this list, to be sure, right? But this is a good start, I think. As a SNIA board member, I'm happy about this. So, anyway, I think this is going to grow, as it turns out, because again, as it gets more visibility, more companies will get interested. You'll notice the presence of the 3 big semiconductor vendors, at least in the memory space. Right? They're very interested in this. Because again, they're supplying NAND, they're supplying DRAM, and if you're going to make an SSD, you're probably going to end up using NAND for sure, maybe some DRAM, maybe some other forms of persistent memory. But I think that's why the semiconductors are in it. You'll notice some of the controller companies are in it too. And then there's one particular company that makes cores that's in it, which is kind of fun. So anyway, that's the lay of the land, at least for today. And by the way, this is all public domain material. This is available from the SNIA, or you can email me or tweet me. I'll send you a copy of this. Nothing proprietary about it. All good.